Beautiful.
Great.
Yeah, much better.
Perfect. Thank you for the feedback. All right. So as Kevin said, what we're going to talk about this afternoon is the practical application of machine learning to cybersecurity. I'll give you just a little bit of a quick introduction on who I am. My day job, as Kevin mentioned, I'm VP of Security Services for Target. Been with Target 6 years now. I've career-wise been in information security well over 30 years, and InfoSec I jumped over to in 1994 when this thing called the internet became. I've had the pleasure to author or co-author 17 books to date, which is a lot of fun. Most importantly, I consider myself an engineer and a maker. A lot of this talk will really be tied to that. I am absolutely not a data scientist, nor do I pretend to be one. One of the things that really excites me about machine learning nowadays is that the really, really smart folks that are doing the data science work have packaged this up nowadays in ways that are very accessible to those of us who have not dedicated our life to being data scientists and can get some fun results, as we'll hopefully see today. And ultimately, I am an unapologetic math and computer science geek. Probably one of the things I'm most known for is I've spent a lot of time on the ground at big breaches, and find it interesting that what gets reported in the media is never what actually happens. It's shades of that. So I want to start off just briefly talking about what I think is just a fascinating opportunity for those of us in computer science, right? Ultimately, breaches grow every single year. 2020 is going to go down easily as one of the most breaches. Of course, this year, ransomware in particular has just exploded. Couple that with there's incredible shortage of folks that do what we do to help companies defend against that. And the other thing, most of us do like to be able to buy toys and put food on the table and stuff like that. And frankly, there is a ton of funding out there if we have new ideas. And I'm hoping that in our talk today, maybe I'll spark a little creativity for all of you at some of these opportunities to apply some of this. So what I've got here is what's known as the Gartner hype cycle. That's what you'll hear referred to mostly. And essentially what this is a graph of is how new ideas happen in most technology spaces, certainly in the field of cybersecurity. So a new technology comes along, that's the technology trigger referred to there in the lower left. And there's this rapid explosion, frankly, an overhype of what that technology can do to help revolutionize and solve the various problems in the field. It hits that, what Gartner likes to call the peak of inflated expectations. And of course, at that point, you've got a lot of companies, individuals who've tried to use this seemingly magical tech, and they go and implement it and find that it can't do a fraction of what all of the marketing hype and the sales pitches said that this was going to do for their organizations, which leads to the trough of disillusionment. But luckily out of there comes usually a middle ground where the hype starts going away, people start understanding the technology for what it really is. And that's where we see the slope of enlightenment up to the plateau of productivity. And that's where machine learning is starting to be today. Probably still somewhere in that peak of inflated expectations and trough of disillusionment. If you decide to go attend RSA's this year and scan through the 900 and some security vendors wanting to sell you products to solve all of your security problems, you will find very few of them are not touting their application of machine learning. Unfortunately, when you dig a little deeper and scratch the surface, what you most often find is they're using simple rule engines or things like that, and frankly, not really the application of ML. But what I'd like to do this afternoon is really talk us through getting maybe a little quicker to that plateau of productivity, because ML is an incredibly powerful technology as a field and has a lot of use, but there's a lot of potholes and impediments on the path to get that useful, and that's what I'm going to try and get folks through today. Was there a question? All right. Well, like I said, don't hesitate to holler if anybody's got a question. So let's start with just a simple briefing on machine learning. My goal here today isn't to make you experts in machine learning, just to give you some foundational understanding. Machine learning, as you can see in this simple diagram, is really a subfield of the larger field of artificial intelligence. AI is much broader than machine learning is. Machine learning really mostly boils down to the application of statistics. As we go through the different ML models and some of the different techniques, and maybe talk a little bit in more depth on some of the specific things, it really comes down to statistics. Now, of course, I am simplifying a little bit, but for purposes of using ML in particular, understanding that it's primarily the application of statistics really, I find, helps a lot of folks sort through some of the decision making. So what I've got here is a diagram of the major types of ML. So essentially, ML breaks down into two large families, supervised and unsupervised. Most of what we'll be focusing on today is supervised, and I'll explain why as we work through this afternoon. As part of supervised, there's really three broad groups: support vector, decision trees, and neural networks. And of course, the neural networks break down into several types of application of neural networks. On the other side, we've got unsupervised machine learning. And that involves really three big branches, and then of course you can all read, I'm sure, the subfamilies under those. So we'll talk specifically about why in many cases supervised works better for a lot of our application, but I want to be really clear up front that some of the opinions I give you, of course, ultimately are just my own. And are also specifically tied to the application use cases, to the types and ways that I've been successful in applying ML for real world applications in the field of cybersecurity. But there's a very good reason why all of these different types exist, and all of them have very, very good uses in the right situation. And that's really the first kind of place that a lot of folks get tripped up with the ML, is choosing the wrong type. So essentially, unsupervised, since you've got some backgrounds in cybersecurity in this class, you'll understand hopefully what I mean when I say anomaly detection, right? Looking for things that are outside of the normal. This is a technique we use in cybersecurity a lot, and really is a good way to think of the unsupervised forms of ML. Unsupervised ML, essentially, we give it a large data source and we use the different types of algorithms in it to let the ML algorithms sift and sort the data. Now, what can be super useful about this for us in cybersecurity in particular is it will often find things that we would not necessarily find on our own. It is a good use for it. However, a lot of the products that try to use ML are using unsupervised, and that would be, by the way, a really good question if you're thinking about a platform that touts using ML, is asking them whether they're using supervised or unsupervised machine learning. to do essentially anomaly detection. Well, the challenge with that is that real-world environments, real-world networks, real-world host environments are incredibly messy. If you go out to look at the different types of mobile devices and the headers from those, or the different packets and data, right? Unless you've got a very, very pristine environment, there's going to be all sorts of anomalies on it. And because machine learning is just mostly aimed at finding those anomalies, what you end up with is a lot of noise in most cases. So it can go out and very successfully find you a bunch of anomalous data. Unfortunately, what you'll find when you start sifting through that is very little of those anomalies are security anomalies. And that's where that first kind of gotcha comes into play, is you'll find that because of that messiness, the unsupervised ML algorithms and applications will find you a lot of anomalies, but you'll spend a bunch of time searching through those with a very small likelihood of finding security problems that you need to care about, right? We've got inconsistent configurations. Vendors write applications often very poorly. Just because a company produces software doesn't mean their engineers are necessarily top of the game engineers. And often what you find is vendors will do very unusual things that will show up, of course, as anomalies. Real-world hosts are unique, right? These are all just examples of where if we used pure anomaly detection, unsupervised ML in many cases, then we're going to end up with a whole bunch of noise that doesn't help us find security problems in our environment. Everybody with me so far? Makes sense?
Yes.
My slide seems to be stuck here.
Yep.
There we go. All right. So the second common failure I've seen in a lot of the platforms are out there is that the products will try to be all things to all people. Let's take an example. If my goal is to build an ML application, say I'm a CrowdStrike, for instance, which is a fairly well-known vendor. They've got an application that runs an endpoint looking for malicious activity, right? Finding the breadth of malicious activity could be malicious Windows executables, could be malicious Mac executables, Linux executables, could be malicious macros and documents, and so on and so forth, right? There are so many ways for malicious activity to manifest itself in a host that using ML to capture that breadth of that is an incredibly hard challenge. Now, I want to be clear, it can be done, but the majority of organizations that accomplish that fail at it, right? And we'll talk about this in more length here in a little while, but when we're determining what the optimal parameters and features for a tightly scoped use case, so let's say, for instance, I'll give a very concrete example. Let's say I want to build an ML model that will tell me with a high degree of accuracy whether a macro in a Word document is malicious or benign. That's a good example of a tightly scoped use case. Figuring out what our parameters and features are, and I'll explain more about what those are in a little bit, is very straightforward process because there's a limited number of parameters that would be potentially used as features in our model. And so doing the analysis to figure out which of those parameters are going to be effective is very simple and straightforward. But those parameters and features are going to be different as we expand the type of use cases. So now if we also want to, and it looks like my PowerPoint crashed. Let me get that back here in a second. So as the use cases expand, so go back to my early example, right, where I was talking about, PowerPoint, I was talking about, you know, malicious Windows executables, malicious Linux or Mac executables. All of those in practice are going to require very different features and parameters to feed the ML model in order for the ML model to determine what it is that that it's supposed to be analyzing. Remember, I said earlier that essentially this is statistics. So those parameters and features are the different data points that it's using to do its statistical analysis against to determine which ones are outside of the norm. And so as those use cases expand, the parameters and features dramatically expand, and essentially what you end up with is an exponential increase in the number of things that the ML model has to take into account, which in turn makes it consume much more memory and things like that. That's why for practical implementation, a lot of the platform companies like CrowdStrike, their actual endpoint agent is extracting a lot of the data needed for the models and actually passing them back to a cloud-based ML analysis engine rather than trying to attempt to do all of that analysis in that local endpoint. There's simply not enough resources in that endpoint to be able to satisfy that use case. Can everybody see the slide again okay, by the way? Double check.
Yep, looks good.
Yep. Yeah, I can see it.
So that's a second reason why often this goes sideways. And part of the reason why I'm starting with some of these failures to look for is because I recognize that a lot of us are not going to make the investment necessarily personally in order to gain the depth of expertise needed to actually build our own ML models. But it's rare that all of us aren't going to be using ML in various aspects of the job. And so ultimately what I'm trying to do here is make sure that all of you are equipped with some ways to think about this, not just for potentially applying it yourself directly, which I would hope to inspire some of you to try, but also to use to help you understand the effectiveness and ask better questions and evaluate some of the technology that you may purchase for use in the various organizations that you work in. And so these common failures are a lot of the thing that we can use to help us understand, but this also lays the pathway for when we're trying to build our own, how we might go about, you know, avoiding some of these landmines, so to speak, as we progress. A third big common failure is to not leverage deep subject matter expertise, specifically cybersecurity expertise. What I see a lot of organizations that are creating these platforms for us do is they'll go out and they'll get an incredibly brilliant data scientist, and that data scientist will use typically pure unsupervised to crunch and analyze the data, and they'll surface a whole lot of things that frankly aren't relevant for the security industry. You know, as I point out here, right, it's kind of hard to solve a problem that you don't understand well. And while they're going to turn up lots of interesting information, a lot of that information, while maybe interesting, is not a security problem. And ultimately, part of the value, potential value in ML is in using ML to really level up our security teams, allow them to use a well-built model to show maybe the best analogy is a boxing one, to fight above their weight class. What I mean by that is I'm going to share a tool that I created a couple years ago in a model, and I call Assimilate. And when I built it, I spent a few months working on the model, and essentially the end goal I was going for was to build something. You know, I've got over 20 years of InfoSec experience. A lot of that is in cyber threat hunting and doing sorts of things that are maybe specialized tasks that a lot of folks don't have experience. What I was hoping to do was to produce a tool and a model whereby we could run it and take a whole big pile of data and pull out just the potentially interesting security things for that level 1 analyst, essentially empowering them to, in effect, punch above their weight class. And so that's really where we need to focus, at least in terms of applying ML for security, right? We're looking for a security problem that will improve security. Because as you can see on the slide here, first, it might be interesting, but not a security problem. It might be a security problem, but that still might not be something that actually improves the security posture of our organization. And so if we bring in and don't leverage cybersecurity expertise coupled with data science expertise, we're very, very likely to come up with common failure number 3. The other thing I see that's frequently this is doing this in a lab, which doesn't have the breadth of noise that a real world network does, is much easier. A lot of the organizations that are building some pretty cool stuff, right? It's actually really interesting technology. Works great in their lab environment, has a high success rate in their lab environment, and then we run it in real world data, and all of a sudden the success rate will plummet. And so those are all part of what I like to call common failure number 3. So let's look at common failure number 4. I don't know why my PowerPoint's being difficult today. There we go. Number 4 is just the inverse. Number 4 is failing to leverage deep ML subject matter expertise, right? There is expertise required to do this. Now, I did say earlier that it's gotten so much easier. It's to the point where someone like myself with definitely very limited ML expertise can be very successful. But to be fair, I spent better part of 6 years learning ML to get to that fair level of capability. And I'm still nowhere near as capable as a lot of other folks out there, for sure. You know, and these are some of the key things that we're going to need to do success, right? We're going to need proper parameter and feature selection. I'll explain that as I said. We're going to need proper algorithm selection. Again, we'll talk about that as well. And we need proper testing and refinement. If we don't do all 3 of those things properly, now, luckily, there's fairly straightforward techniques for all of those, then we are absolutely not going to be successful at producing something that is useful. So how do we do it then? Enough with the negatives. Let's talk about the positives. Well, I like to break things down into simple steps. And so from my perspective, it really is just a handful of steps that are key. One is we want to choose a problem to solve, and obviously we're gonna talk about all of these in more depth this afternoon. We want to decide on an approach that we want to take, right? Do we want to supervised, unsupervised? We need to get appropriate data. This is, of all of the steps, number 3 is usually the hardest. And as we dug into that more, I'll explain why. We need to determine what the proper features are to build our model around, build the tool itself. That's usually actually the simplest part of it. Then we need to test and tune. We'll need to test the model. I'll explain how to do that, tune that model until we get a success rate that is in line with what we're looking for. And at that point, we've won in my book. So I think there's some real keys to success in here. One is starting out with that use case or problem statement, right? The more tightly we scope that, the easier everything else is. The easier it is to find the appropriate data, the easier it is to iterate our tool, etc. Tightly scoping a problem makes it so that we can easily achieve that success. I would say that's the single most important thing that I've seen and done myself that is often seems to be missed for some reason. Then we need to decide on the approach. The approach, similar to that tightly scoped, is really foundational. The amount, the number of algorithms, the types of algorithms, the types of data that we can leverage is entirely dependent on whether we end up taking a supervised or an unsupervised approach. We've got to have the proper data, and the proper data is not just the appropriate data to feed the model, it also is cleaning the data. Easily when I built Assimilate, and I'll go into a lot more depth as we progress this afternoon, I spent something north of 90% of the time, the total time invested, on cleaning the data. Since I wanted accuracy in the real world, I took a month's worth of network packet data from Target's actual network, which is, of course, terabytes of data, and cleaning that, making sure that when I trained the algorithm in what good data looks like versus what malicious data, cleaning all the malicious activity out of that broad network data, for instance, was really critical. Otherwise, the model's training would be inappropriate. Then we need to determine proper parameters and features. This is probably the step that takes the most understanding of application of the ML, but there's some shortcuts there that'll help that I'll talk about, and then testing and tuning. There's no model, I think, that comes out of the gate and just nails it out. It really, if our accuracy on our assessment of our first runs of our model on the test data are too high, then we probably need to suspect that we've got some bias in our data, and that we need to jump all the way back up to that third key to success there. All right, so I'm moving along fairly quickly, still making sense? Everybody still on board? Or
Yep.
have I put everything asleep? All right, let's dive into those then. All right, tightly scoped problem. So I'm just going to seed it with some examples of what I would consider tightly scoped problems. One, find the malicious activity in my DNS traffic that my signature-based detection isn't finding. One of the reasons why ML is so potentially powerful for us in the field of cybersecurity is that a lot of our, especially network-based detection mechanisms, are really essentially signature-based. And so the problem with signature-based approaches is the adversaries, one, the cyber criminals, often, almost rarely, don't have access to see what those signatures are. And even if they don't, it's very simple for them to make simple variations to the attack, to how their traffic looks, to evade being caught by those signatures. Whereas a well-tuned ML model is much more robust at catching a much wider array of malicious activity, or at least potentially, if we've done our job creating the model. And so the reason why this is tightly scoped is because we're looking at a single protocol, DNS, right? And that single protocol has very few headers. There's not nearly as much of a variety of what normal DNS versus abnormal DNS is. Things like that all reduce the scope of the size of what that ML model is going to have to understand about the DNS protocol in order to be successful with that use case. Another example would be finding malicious PowerShell activity in Windows event logs that isn't being detected otherwise. Again, finding malicious PowerShell activity is a really tricky thing. Most organizations, certainly mid-size and larger organizations that have any kind of a foothold of Windows, tend to leverage PowerShell for a lot of administrative functions across the enterprise. And so determining which of the PowerShell activity in a host is malicious versus which is benign and legitimate admin functionality is a really tricky challenge for signature-based approaches to detection. An ML model has a lot more interesting ways to come at that problem. And again, though, very tightly scoped, right? We've got a single series of records, in this case, leveraging event logs for a particular type of activity. It gives us a really nice, finely honed thing to go after for building our model. Another one is finding unknown malicious traffic posing as legitimate applications. This is actually the use case that I chose for my assimilate that we'll use as kind of our case study as we dig in here this afternoon. All of these are tightly examples of tightly scoped problems. And I would suggest that this is the key for success for step one, to come out the other side with a really useful example. I've used one in passing. I'll have links to before. One of our other team members at Target wrote, he calls it Malicious Macrobot, and its tightly scoped problem is this document macro malicious or benign? We run that against all of the traffic submitted against VirusTotal, Reversing Labs, several other feeds of malicious and non-malicious documents. And I haven't looked recently, but the last time I saw the stats, it was running a 98.6% accuracy rate, which is pretty much unheard of in ML model effectiveness rates. Part of that is because Evan started with a really, really tightly scoped use case, and then of course applied a lot of other great capabilities as well to the problem. So questions about that? Does that make sense for the key kind of first step in going with a tightly scoped problem? All right, I'll keep going. Secondly, we need to decide on the approach. And of course, I've alluded to this before. The key here is, do we want to use supervised or unsupervised? Generally, and again, I am definitely oversimplifying a lot of things that are important details, and there's lots of real world exceptions to all of this. I want to be very clear about that. But generally, it's best for solving specific problems. So with specific problems, that would be very tightly scoped use cases like I just gave some examples of. With supervised, we're going to need labeled data. So labeled data is just simply, we need examples of the type of stuff that we're looking for. So maybe if in my case with Assimilate, I had two types of labeled data. One set of labeled data was labeled malicious, and one set was labeled non-malicious. But it can be whatever. It's just two examples of the type, right? So malicious and benign macros, or if we're not looking for malicious activity, right, it might be just good and bad. You know, what we use as the labels is irrelevant, but essentially all of the supervised applications of machine learning models, we need to train it on the two different types of data with the intent of having a model that then can look at data we've not trained it on and tell us whether it's one or the other of those two labeled types of data. And then unsupervised, as I said earlier, is essentially anomaly detection. For unsupervised, you're going to need lots and lots of data. The more data that you have, the better the results will be from the ML models. And that usually is the prohibitive factor for a lot of us, is getting sufficient data, right? As I suspect most of you know, Google uses an unsupervised model on all of the images that are uploaded to Google Images, right? Or scraped with Google Images. And they have the ability to recognize with a high degree of accuracy cats rather than dogs, for instance, and people's faces and stuff like that. To get the model to the level of accuracy that it runs at, which is still only in the, I think the last stat I heard was the high 80s, low 90s percentage of accuracy. It needed petabytes, right, of data to build that. Now, I'm not meaning to say that we always need that much data in order to be successful with unsupervised, but at a minimum, I've never seen something that wasn't really starting to become effective without at least terabytes of data. Then the next step, as I said earlier, is we need the appropriate data, right? So this, of course, is data appropriate to the problem we selected. So if I was going for that DNS use case I threw up as a possible example, then I'm going to need a lot of DNS traffic to feed to the algorithm. I'm going to need, if I'm going to assume moving forward here, mostly that we're going to focus on supervised, since, as I said earlier, that's the approach that I generally lean on and have found most effective for the implementations that I applied ML for. So in that case, we're going to need some known good, and we're going to need some known bad. Now, it's never as simple as just getting known good and known bad. So with Assimilate, for a lot of the known bad traffic, I used malicious or malwaretrafficanalysis.net. Sorry, I blanked on the URL. I've got, oh, by the way, I forgot up front, I uploaded the talk, the videos I'll use for some demonstrations here in a little bit, the deck that I'm using, all on my GitHub page. I've got a link to all of that in the end so that everybody will have access to that. Anything that I'm referring to, I'll have links to at the end as well. So malwaretrafficanalysis.net, super good dude that takes current malware and he posts a page with Pcaps samples of the malware traffic, an analysis of how that how that malware works and looks at the and allows anyone to download it for free. But here's where I'm going with the challenge with the known good, known bad. If I were just to take that data from malwaretrafficanalysis.net and take those bad malware traffic samples, when you open one of those packet captures in Wireshark, not every single packet is malicious. while that's a packet capture of the malware talking, it's also going to be making DNS queries. Almost always, not almost always, that's overly strongly said. It is extremely common for malicious software, malware, when it first fires up, to make a query to 8.8.8.8. Now, hopefully a lot of you know what the IP address 8888 is. It's one of the core DNS servers maintained for the internet by Google for us. The reason the malware is doing that is not because Google is hosting something malicious, but simply because Google's, the malware, if it can successfully resolve to that address, the malware can assume it has access to the internet, right? And so it's essentially doing a, hey, do I have internet connectivity check? We don't want to train our model that connectivity, doing a DNS query to 8888 is malicious, because of course all sorts of legitimate software does that as well. So as part of having the appropriate data to train my model, I had to go through all of those and hand clean out all of that non-malicious activity. So just the actual activity of the malware to its command and control and things like that was what was left in those packets. This is why I said most of the work is in this step. It also applies the other direction. Making sure that the data that we have for good data doesn't have any malicious traffic in it is also tricky. I mentioned Assimilate, the tool I built, model I built. I used a month's worth of real-world target traffic because I had, luckily had the ability to have access to that as part of my job. Well, there was some malicious activity that occurred over the course of a month that I had to hunt down within all of those packet captures and remove before I use that to train the algorithm that this is all good traffic, because otherwise, you know, at the end of the day, the model that we're building is going to learn exactly what we tell it. And so any biases or errors or issues in the data we feed our model are going to show up in how it responds forever. That will train the model that way. So then after we collect that data, we do our cleaning. What we want to do, the standard practice in building models is we take 80% of the good traffic and 80% of the bad traffic, and that's what we use to train our model on. Then we reserve the 20%, so we just take 20% of each of those sets of labeled data, set them aside separately as our testing and tuning set, right? If we've trained the model appropriately, when we run the model against that 20% of good that we set aside, it should say 100% this is good. In an ideal world, it should say 100% of the bad is malicious. And this is how we come at the accuracy for the different types of ML models. So, appropriate data. Everybody still with me?
Yep.
Yep.
All right, great. Hopefully this is still interesting, and I haven't put anybody to sleep yet. All right, now I've been hinting at this, referred to that, I promised that I'd talk about this. What are features? I've said we've got to determine the parameters and the features. Well, features are just simply specific data points. So if we take, say, something like HTTP headers, all of those individual headers inside the HTTP, the overall HTTP header, like a URL, for instance, is potentially a specific feature. Now, it becomes a feature when we choose one of those data points to be included in the model. right? So it could be the user agent. It could be the event ID if we're analyzing Windows event logs, or the DNS query and response in DNS traffic, right? Any of those essentially individual data points in the data that we're looking to build models for are have the potential to be features for our model. Now, the easiest thing to do is to simply choose all of the data points. And indeed, that's actually not a bad first step to run when we're trying to figure out even which algorithm, which way to present the data, which way to encode the data, all of these sorts of things. Often one of the first steps we will do is just try all of the features. But of course, with everything in computers, there's a trade-off, right? More will increase the size of the model, and sometimes more actually reduces the accuracy of the model, not increases it. Because if this is statistics, right, there's a reason why I used a bell curve to represent the idea of statistics several slides back, and that essentially what we're doing with this model is we're looking for our outliers. And what we really want to come up with for the ideal features are features that have a high amount of variability between the good versus the bad, right? So that data point in good traffic looks very different than that data point in bad traffic. And that's essentially what we do. That's what on this slide, what I mean when I say high variance features are essentially what we're looking for. And this is super important to do this. I've got I've also referenced this in the end of the in the end references. But this is an example from a talk that David Bianco and Chris McCubbin did, titled "Practical Cyborgism." They released partnered. So David, if you're not familiar, probably one of the top cybersecurity experts in the world, and Chris McCubbin, hardcore data scientist. So bringing that, as I alluded to earlier, best of both worlds together in partnership, they released a tool called ClearCut a few years ago that still is an incredibly powerful tool. This is a talk that David did walking through. Highly recommend if you want to go a level deeper than we're covering today. This is a graph showing as they were working through to figure out which parameters to use for their features. And you can see the graph variance, how big of a move it went from that mid baseline as they selected different parameters. More depth than we want to cover today for how you actually do that. But it isn't rocket science by any stretch. And I certainly encourage folks to continue this. Then we come to the build our tool step. And for this, I'm a Python fan. Python 3, especially if you're using IPython Notebook, is just a fantastic option for doing machine learning with. Part of the reason I love Python for doing ML work is these three libraries: Pandas, which is for handling huge amounts of data, large data sets; NumPy and scikit-learn. A bunch of folks way smarter certainly way smarter than me have gone out and taken all of that hard work of how do you actually encode these algorithms, build them, and package them up in a way that we can just call them as libraries and use them. So we need to understand what the particular algorithm does in order to use it appropriately, but we don't have to do any of the hard work of actually writing the code, which frankly is well beyond my Python skill set for sure. We're going to need a way to parse the data, right? So I'm kind of talking through, if we've got to build our tool, these are some of the things that we're going to have to build into our tool, right? We're going to have to parse it. We're going to need to select an algorithm to use. Now, one of the algorithms that's really useful for, especially starting out with ML on the supervised, is called random forest. And essentially, random forest is really just an algorithmic wrapper for a ton of other algorithms. And so what random forest does is runs your data through something like, I don't know what the actual count is, I think it's a dozen-ish different algorithms to determine which algorithm produces the most interesting results for your data. So it's kind of almost a cheat of sorts, in that random forest is going to select a whole bunch of algorithms for you in a way that's much easier than doing the work by hand. Like everything, of course, there is a trade-off, though, in that random forest isn't going to be as optimal for performance as whichever of those sub-algorithms actually ends up getting selected for use on your data. But it's a great way to start out. You're going to need a training mode and an analysis mode for your tool. When we walk through my tool here in a little bit, you'll see application of all of that. And then the trainer, often what a lot of folks will do is package this up as an individual. That's what I tend to do. You know, I have a trainer, which will actually build the models and save them out. And then I'll have the assessment tool that will just import the model that was built by the trainer and then apply it to whatever data I want to test for. Again, I'm going to be actually running some of these tools here in just a little bit to give you a better idea in your head of how that works. And as I said, analyzer. And of course, then it's just a matter of testing and tuning, right? So we use the trainer, like I said earlier, on the 80% of known good and known bad traffic. Then we run the resulting model against the 20% known good and known bad to see how well they do on predicting accurately. And this is where we then just kind of go back and forth and iterate. All right, well, let's change the parameters that we selected for our model, and what effect does that have? Let's change the algorithms that we're using and apply them appropriately. Okay. Of course, yeah, well, I said this already. So substitute features, algorithms, right? Then if you've done that, I would say the last kind of piece of advice on this test and tune is, if you've done that and your models are still not performing as you would expect them, as in it's saying a bunch of the bad data is good and a bunch of the good data is bad, then you've probably got a bunch of problems in your training data. And by that, I mean you've probably got some bad that you didn't get cleaned out in your test data, or some good that you didn't get cleaned out, and that's at a level that's creating bias in the model such that it impacts the efficacy of the results. So we've covered a whole bunch of ground. The next phase, what I'd like to do is focus on some application of this. We've been going at this for about 40 minutes, better part of 40 minutes. What's everybody's preference? Should we take a break, brief break, let everybody get up and stretch, keep going? I'm pretty flexible on my side. In case it's not obvious, I could talk about this till I'm blue in the face. So.
I got my coffee pot.
I'm good to keep going.
Okay. Since nobody's claimed the opposite, we will keep going. So what I've got here is an example of why. Now we're going to lean in, and I'm going to kind of focus on essentially a case study of my tool that I built a couple years ago for doing just what we've been talking about this afternoon. And so this is an example of a packet capture from an actual network, and you'll see I've got highlighted there one particular packet. Does anybody recognize what that is? What do you think? Malicious, not malicious? It's just a get to a search.php page, at least on the surface.
Malicious.
Somebody's old enough to
No
make it that. Sorry, go ahead, Kevin.
I don't know what I'm saying. I was gonna say there's no header, but it's just glancing at it.
Not HTTPS, which makes me raise my eyebrow.
That's a great point. So it's in the clear. Any other thoughts?
The host header is incorrect. It's
The host header is, I would say, terse. So it's a great call, Girish, in that and I hope I pronounced your name right, in that it is not what a typical host header looks like. That is absolutely correct. It is actually a valid HTTP host header, but one of the interesting, last year when I got to do a guest lecture and I talked about threat hunting, one of the things I talked about is often it's little nuances, differences between real world and malicious. And this is actually a good example of that. And you're exactly right for pointing it out, Girish, that this is not a standard header. I would say it's valid, it's legal in that it meets the HTTP criteria. It is absolutely malicious. This is a check-in, what we would call a keep alive from a host that has a malicious backdoor running into it to its command and control server. So let me give you another example. What about this one? This one's got a lot more in the header. What's everybody think? It's still HTTP. Somebody be brave. There's no bad answers, I promise.
Is that the get diverts that info which goes us off, or seems to be fishy or scam?
It certainly is a pretty interesting URL, right? Get divorce/divorce.php with some data for sure. This one you'll see has got, a little bit more in terms of it's got a user agent, some other stuff like that. But yet again, another example of malicious activity this is another different family of malware, different agent, malicious agent, I should say, checking in with a command and control. And so probably no surprise, here's yet another example of that. And the reason why I wanted to show a few of these real world examples are, finding these in the midst of an environment is hard. Most of these are not going to get flagged. I mean, they probably now, because these are actually a couple-year-old samples. But at the time I took these packet captures, they weren't being flagged by most of the network detection stuff that was out there, etc. And I share these because this is why I'm just such a proponent of spreading a little bit of the love of ML around, because it has so much potential to help us with some of these really hard problems that you know, it is absolutely worth, in my opinion, the investment in time to learn some of this technology, right? And a lot of this comes back to things that I mentioned earlier, right? We've got a lack of experienced practitioners, so on and so forth, right? And so in particular, I really designed Assimilate as a cyber threat hunting tool. And so Assimilate, what I did step by step was I gathered real world network data. Sorry, I said a month earlier, didn't I? I meant a week. Just a little over 10 terabytes of data. I used, it was at the time, it was called Bro, since Bro has since been renamed to Zeek, to convert the packet captures into metadata. So packet captures are raw binary data. Zeek is really convenient for converting those binary data into text-based data. And that's really useful for us, for ML in particular, because it's much easier to parse text-based data than it is in most cases binary-based data, especially a file format as complicated as the Pcap file format is. And so really Zeek was just a tool to convert the raw data into another. The other benefit of using Zeek is I could do some transformation on that data in that step process, as well as pull out the types of data that I didn't want, right? So a Pcap from a network has all of the network data. In my case, Assimilate only looks at HTTP traffic, or HTTP headers in particular. And so that just gave me a convenient tool to extract purely the HTTP data out of all of the network captures that I had. And then I compiled over a year's worth of packet captures from malware and converted them the same way. So mostly, again, this was malwaretrafficanalysis.net, but I also used some of my own zoo, malware zoo that is, for this process. And similar to what I did with Bro, Zeek, I converted it. Then I cleaned the malicious metadata out of the non-malware activity. That took a lot of time. One is I did it kind of in a multi-step process. So I started with the malicious samples I had and made sure that none of those malicious samples were actually in the traffic I intended to use for known good. Then what I did was, for that week period that occurred, I looked at all of the malicious cases, so all of our CSIRT cases for that week, found the corresponding activity in the network traffic and pulled that out as well. And then I spent probably more time than I would care to know just hunting in the remaining data for anything that looked fishy or malicious, and I definitely found a few more oddities in there that weren't the sort of data that I wanted to train. This step was easily well in excess of 80% of the time investment that I made around Assimilate. Then, I explained that already. Then I began testing for what algorithm, what parameters, and what features I wanted to use. I had a working theory, as you might imagine, going into this, that naive Bayes might be a really interesting algorithm and potentially really useful algorithm for analysis of HTTP headers. Now, all of you have naive Bayes used on your behalf every day, whether you realize it or not. Anybody know what naive Bayes is used most commonly for? No guesses?
Not a clue.
It's used for spam filtering. So naive Bayes is the ML algorithm that is at the heart of spam filtering of email. It's designed specifically for analysis of language-based text. And as it turned out, I was able to get well over a 92% accuracy rate with Assimilate using naive Bayes algorithm. So my going in theory turned out to be correct as I analyzed it. So then I coded the trainer and the model applications, and of course tested and iterated. And where did I lost my icon. There it goes. And win, which winning for me isn't necessarily a beer. I'm more of a bourbon person, but inevitably winning in my book is celebrated with an adult beverage. All right, so let me run a demo of Assimilate actually working. Any guesses, by the way, as to the origin of the name Assimilate? Some of you must be sci-fi fans, surely.
The Borg.
Star Trek from the Borg.
Exactly. I am a geek. I am proud of that status. All right, so I'm gonna try playing a little video here so that I don't, and this is the actual tools and stuff running in action here. So you can see I've got 3 Python programs. This is all, of course, up on my GitHub. The models, the pickle models are not there because unfortunately, since I did use real world target data, I can't share the actual models themselves, but hopefully you can do that. So I'm running Python assimilate assess against that log file. So of course, the first thing it's doing here is loading in those models. When scikit learn, they're called pickle models. And I'm jumping through this fairly fast here so as not to completely bore you. But you'll notice every so often it's reporting out, oh, hey, I've got something here that looks suspicious. So essentially, that was an individual HTTP header that had enough of a match to the bad of the model that it indicated that it was suspicious. Now remember, my goal in this was not to use it really for real-time detection. My goal in this case is to use it for hunting. So that log file there is essentially a Zeek converted HTTP header log from actual network traffic in the target environment. And it should be done here shortly. And then I'll pull up the resulting output log file. There it goes. So all of this gets written out into a local log file, which you can see me opening here with TextMate. Turn off the word wrap in TextMate here a second. And so these are all of the, in this case, 46 entries from that particular set of network data that Assimilate said, hey, you might want to go take a look at these. When I did, about a third of it turned out to be malicious in nature. And interestingly enough, lined up pretty well with that day's CSERT casework for malicious activity. But pretty simple, right? Straightforward. That's kind of the beauty of the upfront work that was done to build the model, to build the tool, is really where the complicated part is, right? The actual then, use of this after that is pretty straightforward. So what did you just see? Well, as I said, Python script. It used train naive Bayes algorithm base model against just over 37,000 HTTP headers, 46 things that look suspicious, which has a suspicious rate of 0.12%. So in other words, 46 of 37,440 is 0.12%. So what do we need to actually do this? As I said, it's all up on my GitHub, although I should have updated that slide to say Zeek instead of Bro. So Python, scikit-learn, and the pandas Python modules. I did use NumPy as well. I should call that out. I needed the packet captures of the non-malicious activity, as well as packet captures of the malicious activity. I used Zeek, which is open source, free software. Now, I did use a special Zeek script called HTTP header. That's not part of the normal Zeek packages, or at least it wasn't at the time. That is included, so that script is included up on my GitHub as part of with the other stuff, because ideally, I'd love everybody. One key thing that I will call out though, I wrote this a couple years ago, and I have not yet gone back and refactored it for Python 3. It is written in Python 2.7, which of course has been deprecated as of the beginning of this year. So you might have to go hunt down 2.7 versions to execute it. I've got it on my list to update to 3, but I haven't quite gotten there. Oh, I started to say, so the reason why I did the HTTP header script, HTTP header as compared to the HTTP script for Zeek, takes the entire header and concatenates it as a single line. And I found that incredibly convenient for parsing the data and focusing on the particular features that I wanted to tie my model to. I could have simply post-processed the HTTP script output from Zeek and accomplished the same thing, but luckily I know how to do Zeek scripts, so I just did it in Zeek. And so step by step, right, this is kind of a reiteration of what we've been saying already. You know, collected, I actually started out with collecting the training data. Then I trained the model so that I could assess it against actual data files, hand validated suspicious entries. That's how I did a lot of my analysis and tuning, and retrained numerous times in that. And of course, ended with an adult beverage as usual. So, as I mentioned earlier, malwaretrafficanalysis.net is a large source of where I got a lot of the training data to use for malicious data. I also used a bunch of internal malicious traffic, as well as I've got a pretty extensive malware zoo that I maintain personally, and took some choice samples from that. In particular, the reason I use some of them from my zoo is I've got some of the more sophisticated adversarial traffic that's not necessarily readily available in the public that I wanted as part of the model and testing. For the normal data, I just use good old Wireshark, just collected lots and lots and lots of packets. And of course, from there, I converted the malicious data into the text log version using the Zeek HTTP header, as I mentioned already, normal data the same way, into the labeled data, which I then separated 80% of it for training purposes, 20% for test data. And I'm just giving a few to reiterate some of these just to help kind of make it all, hopefully, come together and make reasonable sense for all of you when you're hopefully rereading or some of this later. Few details that I needed to do, right? I had the processing of the packet captures. I had to install that customized HTTP headers module. And then essentially, I literally just use bro-r, that would now be Zeek-r, and that just read in all of the Pcaps and converted them to the output log format. This is actually the custom script that I used for Zeek. Pretty straightforward. Again, this is all up on my GitHub. And then this is the shell script that I use to do the raw conversion, right? So essentially, I created a shell script that said, hey, look for all of the Pcap files and send for each one of those local .pcap files, right? I just had a big directory with all of these Pcaps of all of these different types of data, right? I did a do name equals that individual file. I extracted the name, you know, the .pcap off of the file name, created a subdirectory, and then I did a, as I said, a bro-r against the file. And then I moved the 2 log files I wanted out into a separate directory, and then cleaned it all up so I could cycle and resort, right? When you're dealing with terabytes of data, you're going to want just some simple things like this for scripts to just help you brute force through all of this heavy listing to convert and analyze all of this data. And so then let me show a demonstration of what that looked like processing the Pcaps. So in the upper window, I've got the directory there. You can see a bunch of those Pcaps. I fired off that script I just showed you rather, and you can see what's happening is it's iterating through each of those Pcaps, creating an HTTP log and an HTTP headers.log file, which is the post-process version that I'm using, that I'm going to subsequently use, I should say, to actually train my model. And so then that looks like this. So now I've got those Pcaps that I've trained. Remember, I've got the test data separated here. And so actually, I'm going to pause it a second after it gets after I type the command line. Oh, this is just the help screen. So you can see the train here. Oh, now I'll pause it. There it goes. So I did the help just so you could see the parameters that it was looking for here, and then I'm going to run it in the next step. So notice I put a -n with the folder holding my normal data, which I really creatively named assimilate underscore normal, and then a -m and my malicious data, which is assimilate underscore mals. Again, really creatively named here. And then I need to give it a name, potentially I should say, I can give it a name for the vector file and the base file. Otherwise, my program has defaults. And so you see it read that in. It vectorized the data, which is the process of creating the statistical model, which is then written out. And you'll see up in the upper window, the vectorizer.pickle popped up. PKL is 2.3 meg in size. Oh, no, sorry. It updated a little bit bigger, 560 meg in size. And the naive Bayes train model is 239 meg in size. So those are the actual files that hold the models that were created by this training on that normal and malicious data. So just a few things as we're getting towards the end here that I would throw out. More data generally is going to give you more accuracy. But bear in mind, especially when building the models, more data also is going to create potentially a lot bigger models. And the bigger your models are, the slower it's going to be for processing. Now, of course, there's all sorts of things we can do to help optimize with that, right? The bro header normalization itself is an example of the kind of gotchas that you want to be aware of. So Zeke, bro, and I've given them crap about this forever. I happen to be friends with a couple folks over there on that team. One of the things that Zeke does when it reads in the Pcaps is it normalizes the headers, and when it normalizes the headers, it capitalizes everything. And the problem with that is sometimes capitalization variances are critically important. So you need to be aware that of what all of your tools are doing to the data that you're using. Because if I wasn't aware that Zeke was doing this, potentially that could be resulting in killing a bunch of the efficacy of the model's ability to determine malicious versus non-malicious, because Zeke is filtering out that variance before the model can use it for training and use it for assessing. And of course, as I mentioned before, the tighter we scope our use case, the easier this model is to build, and of course, the more accurate we're going to be able to get it. So then, last but not least, I'm going to show, I've got another video here, which is me running the actual resulting model. Again, I'll start with a simple help, right? In this case, we've got to have the output file that we want any outputs to go, the header files that we want to read in. So this would be the real world traffic that we want to assign. We could have it an individual file, or my tool supports having a directory full of those files. And of course, the model files that we built earlier in order to run that. So you may be all sitting there and going, wow, this is crazy hard. This is, I could never do that. Well, I wanted to end with, this is the actual code from my tool, all of the actual code to build the models and create the assessment, right? Now, it's this small, to be clear, because scikit-learn and pandas and all of these great tools that we've got. But if you go out to my GitHub, you'll see that these tools are not a ton of code. And you can use other people's code and your own to build models. What I'll tell you is I get a lot of reach outs from folks that have seen different talks I've done at the years. So I originally wrote this for SANS Threat Hunting Summit and presented a talk on this there. And so a lot of folks find those on the SANS website, and I get regular conversations with college students in particular, wanting to apply this and et cetera. And it is absolutely within reach. It is, like everything, it takes some effort, it takes some learning and skill development on your part, but the result is incredibly powerful. And certainly, when we think about our own careers in this field, absolutely an incredible differentiator still that is super helpful for helping you land those roles and be successful in your job. So here's a few of the better ones out there. I include Assimilate, Clearcut and Malicious Macrobot are both much better than my work, candidly. Some recommended resources that I've got, the malwaretrafficanalysis.net. I can't recommend highly enough the work he does just over and above in his spare time to help out folks like us is super cool. And then here's my contact, my email. As I mentioned, I put all of this up this morning on my GitHub page. So the videos, the PowerPoint deck, everything's out there. Best way to get a hold of me is LinkedIn. Please don't hesitate to reach out and contact me there. And with that, questions, or did I fry everybody? No questions? I explained.
No questions. Thought it was super interesting. Definitely didn't comprehend all of it, but it's really cool to see how some of these things are being applied in the real world, and machine learning and network stuff is kind of a foreign area to me. So I love learning things. So it's been, thank you for taking your time to show all this stuff to us.
Truly my pleasure.
Yeah, it definitely piqued my interest in ML. I guess one question I had was, how do you deal with false positives?
Well, so that's a great question. False positives are, first, let me step back. False positives are really mostly used in real-time detection, right? So we're doing something and we're getting maybe false negatives, i.e. we didn't detect something we wanted to detect, or false positive, we detected something as malicious that's benign, right? Certainly the concept still applies in ML, but we never achieve 100%. There's no ML model that is 100% effective. The best I know is Malicious Macrobot, which is in the high 90s. Generally, an ML model is considered effective if it's north of 85 to 90% accuracy. So that means something in the neighborhood of 10 to 15% are going to be false positives, right? And with tuning, you know, I was able to get assimilate to about 92%. 92.8 is the best I was able to achieve with it on real world traffic. And so I suggest that ML is much more useful for hunting. And why I say that is because that's probably still not accurate enough that's probably too many false positives if you're going to examine every single one of these. But if instead you're using it as a second layer of defense, where you're going, hey, I want to see all of the stuff that my network real-time detection didn't flag, and do essentially a diff between those, right? So, oh, yep, here's all the stuff that, in this case, say, Assimilate found. Here's all the stuff that maybe we're using Suricata or something like that in our environment that they found. Pull that out and just then examine that difference. That's a good example of how I would apply this in a real world environment. Essentially, because it's such a different way of analyzing, that's, I would argue, true defense in depth versus, say, maybe just having two real-time detection engines. Does that make sense? Kind of answer your question?
Yeah, that definitely makes a lot of sense. Thanks for going so deep into the subject. Also, I really appreciate that you shared some resources. Like it would be super helpful to, like, you know, start out like a weekend project or something like that.
Yeah, I would suggest that, certainly my pleasure, but I would suggest start with actually Evan's Malicious Macrobot, because the cool thing about Malicious Macrobot is because Evan didn't use any target traffic, he's Dockerized it all, and you can pull down the Docker container. It has the models, everything. You can literally be running it in 5-10 minutes from downloading it. On real macros, document macros and stuff. So that's the one I would absolutely start with, is Malicious Macrobot. Evan made it incredibly easy to get up and running. Of course, he's about 10 times the coder I am. So
Awesome.
Other questions?
Hello, Tim. This is Girish. Your talk is as always very wonderful. I had one question regarding the model.
Yeah.
Let's say tomorrow we come out with some new header type in your
Mm.
HTTP traffic.
Yeah.
And then we come to know that, okay, there are some type, those values can be malicious and something to be good. How are you going to, like, is there a way to update the model or you have to start from the scratch?
Yeah, no, that's a great question. You absolutely can update the models. Yeah. So all of the scikit-learn modules and algorithms have mechanisms for taking existing models and then additional labeled training data, and then adding that to the model. So over time, that's how most of the commercial products actually get better and better and better. Is that they'll continue to, they have data science folks who are focused on, okay, what did we miss? Oh, look, there's this new malicious technique out there. So they call the appropriate labeled traffic, et cetera, and they just update the model. Yeah, absolutely, you can, for sure. That's same thing with naive Bayes in particular has been designed for that. Of course, the spam authors, have been at this, something over 20 years that they've been trying to wheedle their way into our inboxes. And the fact that they're still having success is because they continue to get creative about bypassing the models, and the models continue to update. And bit of a cat and mouse. If you were to take some of the 10-year-old models and run them against today's spam, for instance, they probably would detect next to none of that. So absolutely great question. Yeah, definitely something that needs to be done.
Thank you.
I probably should include that into the steps and mention the need to continue training. Other questions? How are we doing on time, Kevin?
Doing fine.
Okay.
Hey, Tim Anand here. Quick question. You mentioned, this is used for hunting, and can you tell us like how much of it, or in terms of percentage, right? How much of it is really helped to prevent and detect a target?
Yeah, I don't have any way to give you any reasonable amount of that. I can tell you that not assimilate, Malicious Macrobot, and some other ML is absolutely being leveraged as part of our defenses. It's really, though, more about the depth than any individual pieces. What I would simply say is that it's a critical component, but no more important at the end of the day than some of the other tooling and stuff we've got, or I think most importantly, the crazy super skilled people that we've got on the team. That at the end of the day, I'm certainly a believer that tools will always just be tools, and most of the biggest amount of the outcomes that we derive in terms of value are because of the skill of the people, rather than the tools themselves. But the tools do matter, right? What I would say is that I've definitely had some fun success taking some entry-level cyber folks, partnering with them for a week and using tools like Assimilate to find some stuff that, part of what went into that model came because of some of the expertise that I've managed to build over time, right? And they get to take advantage of a little bit of that. So a help, I would say, but just a piece of it. And I don't know how you would equate that to an effectiveness, unfortunately. Not trying to dodge your question. Great question.
Yeah, that makes sense. Yeah, thank you.
Absolutely, Anand.
So I have a question, as John. You're talking about improving the model, and part of that is obviously you're trying to detect your false negatives and get them to be found. So I'm just wondering how you strategize around doing that in terms of the training. I guess you know you have the you have to know up front what your uh, ones are that you're missing. So how do you find those, and how do you strategize around knowing what those are? Because the model's not going to tell you them.
Right. That's right. No, great question, John. I would say that there's actually one of the values of the unsupervised use of ML, right? In the short version of the answer, I would say, John, is that you've got to use a bunch of tools, right? The core thing is with false negatives is you've got the you don't know what you don't know problem, right? But you help chip away at that by using a bunch of different tools, right? I use certainly not just my own expertise, but other tools to find different things that were potentially malicious in this case, since I want to weed out and identify any of that. But that's also why I used things like my own malware, Zool, et cetera. I was very intentional about curating malware samples from a wide, that used a wide variety of techniques and approaches because, you know, essentially the model's going to detect, ML is really, really good at detecting things that are similar to things it understands, right? It is terrible at detecting novel things, things that are unique. And so essentially what we've got to try and do we never solve that problem, John. You know, that is absolutely, we've got to go in knowing that that's always going to be the case. And that thus, importantly, trying to minimize it is essential, using techniques like a lot of different types, a lot of different tools to spot, so on and so forth. And then that's also, I would say, where the retraining comes in as well, right? Where I absolutely have had lots of instances. One of the most critical things you do if you're dealing with very sophisticated adversaries is every time you get something new from the sophisticated adversaries, you take it and run it against everything you've ever collected, because what that's going to do is going to show you things that you had previously but that you didn't recognize. And often you may have a sample that's 2 years old, you've spotted them doing something now in the present time, you run that technique against your old, and then there's a cluster of other new things you learn around that, and then you go back the other direction. That's why getting the opportunity to deal with some of the hyper sophisticated adversaries is so interesting, is you've got to use this recursion back and forth because you know at any given time that it's extremely unlikely that you know more than a small piece of what you're trying to ferret out. And if you know that you are only maybe knowledgeable of 5% of the entirety, then that creates an incentive for you to have processes like that recursion back and forth. You know, at one point in my career, I was in a role where I got to duel with a lot of the Chinese nation state actors. And that was the technique that allowed us to move so quickly, is that every scrap we'd find from them doing something on a host, when we would take that against everything else we had collected that we thought might even remotely be them, a bunch of new things would fall out in the old data that we had not recognized previously. And almost always additional things around those that we hadn't spotted in the new that we could then run back forward. And that's a critical kind of technique for getting at at the false negative, right? But with the realization that I think the key there is just that we go in assuming that there's some level of false negative, and it's probably higher than we would prefer, and being diligent that way. I'm surprised at the number of teams that don't keep a corpus of all of their old activity just so they have the ability to do some of that stuff. It's pretty important. But great question, John, really great question.
Yeah, and I love that story about how you're going back through the data to discover new new features to sort of include or look for in terms of the target data, and I'm sure that can be applied to a lot of different ML problems as well. So
Yeah,
thank you.
Yeah, absolutely. Any other questions?
Hi, this is Michael. I was wondering if your model assigns a certainty to any of its results.
Some of the algorithms do support a certainty. It depends on the algorithm. Most of the algorithms have a way to get at essentially a confidence score. I don't tend to use them. I tend to pick a threshold. So what I'll usually do is, now when I'll often use that data when I'm training and testing and tuning initially, but typically once I kind of settled a model into a point where I want to start using it, you know, in kind of real world applications, I'll typically take a threshold and peg the threshold in my code, and anything over that threshold spits out. But we absolutely can get at a we certainly can get at a kind of a confidence score, a certainty, as you asked. Yeah, great question.
All right, thank you, Tim. Let's take a, let's say 10-minute break, and we'll come back and get started with our second speaker, Mike Hughes. All right, let's get back to it. Mike, are you there? There you are.
I'm hanging out here in the background.
All right. Well, everybody, let's welcome Mike Hughes, also from Target. He's going to talk about scalable, right?
Yeah, we're going to talk a little bit about modern automated attack traffic and the scalability of it and what that looks like. So go ahead and get started up here, and you can let me know if I'm sharing out effectively. Okay. Come on. I think I got the wrong screen. Hold on here. All right, is that coming through okay? Perfect. My Zoom controls here, just a sec. All right, I'll keep the chat window rolling here so I can watch for questions in the background. I appreciate the time today, everyone. Thanks for having me. Thanks for inviting me, for the opportunity to share a little bit with the group. Today, we're going to talk about what is becoming probably one of the foremost challenges associated with cybersecurity teams, specifically response operations and prevention controls. As the cyber threat landscape has changed, we've seen a lot of different things occurring in terms of moving away from individual one-off attacks, individual direct hits to organizations, and things that are becoming about sustainable, ongoing engagements that attack the organization in an ongoing and sustained fashion. So we're going to talk a little bit about that today. Kind of some of the ground rules. Let's see here. Come on, cursor. So some of the ground rules for today. I'm going to talk a lot about retail and commerce because that's where my background is. Everything we talk about, though, is going to be applicable to multiple areas and basically anything that you could expose on the internet. If it's an API or a UI-based web page, anything that you're creating, that exposure there is going to be something that is at risk for automated attack traffic. So as you think about the conversation, I'm going to try to weave in where I can call out like a nod, like you might see a nation state actor do this, you might see the kid in his mom's basement do that. I'll try to weave some of that together, but certainly try to apply the concepts as we talk about them more broadly and go from there. I do invite everyone to engage and ask along the way. So I've got the Zoom chat window floating up if you want to ask questions as we're moving through the presentation and you don't want to speak up, certainly throw the question in chat. I'll try to catch those as I'm paying attention. Also, feel free to interrupt me. I want to invite that we do this as kind of an open engagement through the conversation. With that, who am I? So I'm Mike Hughes. I'm about 20 years now, a little over 20 years in technology and cybersecurity. I started as a network engineer early in my career. That's a commonplace for a lot of security professionals. That has changed now. We see a lot of people starting in the development track and moving into security because the nature of how IT infrastructure works has changed. But 20 plus years ago, if you were the network guy, you were the firewall guy, so you were the security guy. That's just kind of how that equation worked, and then it's evolved through those times. Currently, I'm the senior director in the security solutions group. So you actually just heard from Tim, who I work for. Prior to that, I've got quite a diverse past. My company prior, I spent about 6 years at Starbucks. So I'll lean on some of that knowledge here as well as we talk through the conversation today. So what are we going to talk about today? Well, we're going to talk about the automated attack methods and landscape against sites and how that kind of scalable attack and what that means against modern IT components and infrastructure. So it used to be that you had individual threat actors. Well, you still have this, by the way. I shouldn't say used to be. You have individual threat actors deploying code and malicious malware against organizations in an attempt to do things like ransomware, remote code executions, escalation of privilege in some way, to be able to gain a foothold and to be able to do things that are kind of like smash and grab type attacks is the best way to describe those. So you can think about like, we obviously had a problem 6 years ago, stolen credit cards from Target, or stolen identity and detail information from Equifax, or the Sony data breach, stolen corporate data. Very much a one-time hit. They may leave themselves a backdoor in it. The pivot that we're seeing in the landscape in the last 5 years, though, you're starting to see sustained attacks that generate income on an ongoing basis. And that's done through a lot of automated techniques and tactics. So OWASP, for those of you that aren't aware, Open Web Application Security Project, OWASP basically publishes a list of attack vulnerabilities as they document them. They've actually got a list of 21 vulnerabilities that are specifically assigned to automated attacks and automated attack premises. So this is only, gosh, I think we're in our third or fourth year that OWASP has identified this this new automated attack set and started to apply it. When it first came out, it was 10. They've continued to expand it. I'm going to be focusing on a number of the retail cases today, because that's obviously where my background is right now. But these will apply basically anywhere across the board. We'll talk about some of the defense technologies that are put forward, and we'll also talk a little bit about some of the attack tools that are used to exploit what's taking place within the environment. Most common attack methods that we're going to see in a revenue-based sector like retail or financial services is credential stuffing. This is taking a stolen credential that we found, that the threat actor found, not we, threat actor found at another data breach. So maybe Sony is a good example, you know, credentials were stolen there. Yahoo was a good example, credentials were stolen there. And they take those and they shop those to various sites through scripts and tools. We're going to talk a little bit about those tools today. We're going to look and see kind of the ease of use associated with the tools. We're also going to talk a little bit about some of the other attack types that are available. So you have things like card enumeration. So this is the ability to enumerate through stored value cards. We'll talk about what those are today. We're going to talk about PIN enumeration, stolen card validation, and inventory resale or scalping. So these are some of the kind of core areas and automated attacks to the website. So as we kind of talk about the definition here a little bit, what is ATO? ATO at its basic level is account takeover. It is an attack against the user. So we're not exploiting the system in this particular attack type. We're exploiting the weakness of the user and essentially their reuse of passwords. It's become a huge problem across organizations, both large and small. It is relatively easily launched, and it is a we'll say a consistent way to gain about a 1 to 3% access rate against systems. So I'm sure if we took a poll of honesty, a blind poll, I think almost every person in the Zoom meeting today would answer back that they have reused a password, that they've reused a credential. A lot of people have these interesting notions of, well, I just have one for banking, I just have one for retail. That does not help. Those passwords are still then exploitable as the data breaches occur. The other thing that's really interesting here is the exploitation of the site logic. So this is not an attack as we would think about it. This is not Metasploit or some other tool being brought to bear via a custom malware tool. Metasploit, for those of you that aren't aware, kind of a generic tool for performing, it's a framework tool, obviously, for performing attacks against websites and things of that nature. But in this particular instance, the users are actually coming directly to the site, not attempting to perform injection attacks or things of that nature. They're actually just trying to use the logic of the site. They're just going to knock through the front door as we designed the thing, and they're going to go for broke. When I talk about things like site, you also need to think about the context of how the attacker will look at your code. So they're not going to look at it in the context of, I'm going to click here, I'm going to pull this contextual menu, I'm going to navigate to here. They're going to look at the underpinnings, and they're going to go direct typically to the REST methods that are available or the site logic that sits in the back end, and launch the attack directly against those components. They don't need to deal with the front door itself. They're not a consumer. They don't need the graphical interface. They have anything, you know, it used to be things like Phantom.js and Selenium and GeckoFX, and now there are more advanced tools that literally just remove the need to even have the fake browser going forward. And we'll look at that a little bit today. But as the attack has evolved, it continues to focus on the site logic. The other thing that makes this attack so desirable to the cyber criminals is it's a stable income flow. So ransomware against a corporation, if they pay, might be a large sum of money. You may get 100, 200, 300,000, $1 million from an organization if it's large enough, but you're only going to get that as a one-time payment. What the threat actors are doing here is they're building stable income streams that are based around the logic that we've built into our applications and into our sites. So with that, let's talk a little bit about the user. Let's talk about ourselves, right? First and foremost, we gravitate towards ease of use. Complicated sites and things, we just we're not interested in. If it's difficult and hard, we'll go to the next site, we'll go to the next place to do business or the next place to order our food online. The other thing is we're just not good at passwords. We've got a lot of them to remember. The average user has in excess of 50 passwords to manage. It's actually closer to over 100. And so that level of complexity that we need to understand and keep somewhere, we either need to record it. I quite honestly, I'll be just fully transparent. I tell my parents, write it down on paper if you don't have anywhere else to put it. At least they got to break into your house to get the piece of paper. Don't put it on a text file on your computer, you know, the basic kind of stuff. But people just can't remember 50 or 100 password values. And part of the problem is the security organizations have given bad advice. We did this and NIST was part of this, right? So National Institute of Standards Technologies, there were these frameworks around passwords. And we started to say these really complex things to the user. We started to say things like, you need 3 of 4. And at a security level, what do we mean by that? It means you need an uppercase, a lowercase, a special character, and you need a number. You got to have 3 of the 4 of those or the password isn't valid. And we need you to have at least 8 characters. And that complexity, what we were looking at the time was the notion of the ability to crack or enumerate through the password, to be able to randomly guess what was the entropy associated with random guessing of that credential and how far could we get. What was interesting is we actually also built a control that defeated that attack early on. We said things like, you know, 3 password attempts or 6 password attempts and we lock your account. So we built a control for dealing with the issue at the same time we created complexity for the user. We also said things like rotate the password every 90 days. All right, we created these just tough paradigms for the user. So if you've got 90 days, high complexity, high rotate, or and a default control that locks the account in the event of an attack anyways, you're creating friction for no reason to the user. NIST has actually revised the guidance on this recently, and if you take a look at it, we're now talking about less complexity of the special characters and things of that nature, maybe a little bit longer credentials, so you can start to think of like a passphrase or things of that nature, and letting the password sit for a longer time. Basically, we're trying to nudge out this behavior that we ingrained in the user. The other notion or thing to think about is users' brains don't scale like a computer does, and this is where automation starts to play. Computers are phenomenal at directed tasks. If you think about public cloud infrastructure and our ability to scale laterally, our ability to spin up multiple containers, multiple VMs, and then to be able to task them off, you're essentially force multiplying in an exponential way your ability to make attempts. The user doesn't have that same ability in terms of memory. We can't commit that kind of information. And because of this complex paradigm we've created a situation where we're actually enabling the scalable infrastructure to move at a much faster rate than our brains themselves can work at. The other couple of things that are hanging out there in the user's mind is websites are secure. It's not my problem, right? We all think that. They got security. But what they're not realizing is that the attack is actually against them. The attack isn't against the site. It's against their inability to remember complex passwords in these paradigms that we've created for them. The other thing that consumers tend to think about is my credit card company will cover any loss. They're right. There's a law out there and it says that if your card is stolen, loss is prevented or loss is protected, your minimum loss is protected. But things get a lot weaker when you start to talk about card not present, and also when you start to talk about some of the other payment instruments that are available. So let's talk about the payment instruments a little bit. Back in the day, these were very simple things. 20 years ago, you know, it was currency, it was paper, it was coin, it was a credit card, it was a check. These instruments were brought to companies, and they were brought to companies with the understanding that the person bringing them in the door was an assertion of identity, right? So if I, Mike Hughes, walked in the door with a credit card that said Mike Hughes and I had a driver's license that matched that, or a check and a driver's license that matched that, I was taking, I was presenting kind of a strong assertion of who I am essentially to the merchant. Same thing when it goes for the kind of the fraud features, right? They're well understood. We all know about the strip and the $20 bill or any of the $100 bills, things of that nature, and the position of the strip and tearing them apart. Now we have inks in the money and things of that nature. The other thing that was really interesting about hard currency itself that really made it less desirable from a fraud perspective, the dollar increments haven't gone up with inflation, if you've noticed. So I'm going to date myself. I'm obviously, I've been around the earth for a little while here, but when I was a kid, a $100 bill was the maximum you can get. And today a $100 bill is still the maximum you can get. So from a criminal perspective, that particular instrument is just not as desirable as it once was. Same thing, checks. Checks go through pretty heavy scrutiny. There's a lot of validation of the assertion of identity, and there's a lot of validation that the funds are there and that the check can pass. Credit cards have gone through this really interesting evolution where for those of you that remember, we had the knuckle buster back in the day, right? You put physical card in, you put the carbons down, you swipe that impression roller across the top. You knew that the card was present. The numbers had to be, they were basically embossed with inside the card. So there's a manufacturing component to trying to make a fake card. And now we've moved towards this pin and, or chip and signature, I'm sorry, method in the US, chip and pin inside of the EU and most of the other countries in the world. But we have some type of a stronger validation and assertion of that card number. The last payment instrument, because it's the holidays that I got to make nods to, is the bearer bond. Most notably made famous by movies of the 80s. If you haven't seen Hans Gruber fall from Nakatomi Plaza, you probably don't know the story of the German or of the negotiable bearer bonds. The payment instrument doesn't really exist anymore in the US, but it was a cash-like equivalent. If you held the bond, you held the money. There wasn't a register somewhere of these particular payment instruments. It was something you needed to hold in your possession. I'd be up for a spirited debate about whether or not the movie is a Christmas movie. I personally believe it is. Let's talk a little bit about the transaction types and how things used. So these classical payment methods, traditional payment methods, you walk into a store, you present them, or they're mail order, right? You're gonna write your check and you're gonna send it away and money and a product's gonna be shipped to you. You're also gonna do some over the phone stuff. So you have credit cards that we use over the phone, but still buy and ship paradigm, not really real time, right? There's definitely a give and a take that allows some additional controls because of the latency and delay that's associated with it. ACH is a little different. Money moves very quickly in the ACH framework, but now you're talking to a bank teller or you're talking to your bank on the phone, you're going through additional security checks and procedures. So now that we've dated ourselves and we've talked about this legacy cash paradigm, let's talk about what we've done to enable this kind of next generation of what's taking place and why organizations are being come at so strongly. We've moved to a modern payment infrastructure. So we have moved away from this notion that we need to have hard currency, that we have to be able to present something in order to do a transaction, right? So now we're talking things like gift cards, digital or physical. We're talking stored value cards. This is the ability to load currency with an organization. The best example of this I can give you is Starbucks. Starbucks uses a stored value program. If you buy with their mobile app, you attach a Visa card or a MasterCard or an Amex to that, and then you load that card with the money and then you spend the cash. It's essentially a banking transaction with them. You can buy things with loyalty points now. I can buy things with my airline points and hotel points and not just goods and services with them. Excuse me, I can buy goods and services with partner merchants with that they have relationships with. We obviously have the Google Pay and Apple Pay wallet technology, and then you have things like Bitcoin. And what's interesting about all of these is they've taken away the notion that the instrument itself is the protection. What they've done is they've taken that notion that the controls of the payment instrument, so the strip inside of the the dollar bill or the chip on the credit card. They've taken away the notion that that is the protection. And what they've done is shifted the protection mechanism to the account itself, or the system's logic. So when we talk about things like account takeover now, you've essentially, quote unquote, defeated the fraud mechanisms. Even when you talk about things like Apple Pay or Google Pay, they're using a credit card, but you don't have to touch the payment instrument anymore. All you have to do is touch the account and gain access to that. And from there, you now have the ability to launch and scale your attack out. So what does a modern transaction look like? Well, there are the digital wallet payments, obviously, points for goods. We've also changed how the transaction happens, right? I can order online and I can pick it up curbside, or I can have it delivered. This means that an attack against an organization that's a digital-based attack with a Smurf that goes and picks up the goods at the store now, or your runner that's going to go pick up the goods at the store, that can happen in minutes. Whereas before, when we talked about the notion of making an order on the phone or catalog order or things of that nature, you had 12, 15, 20 hours to do a digital fraud analysis and then try to stop this transaction. Now, because of our pickup methods, you can't, right? I can get Amazon Prime Now delivered. I can get Uber Eats delivered, right? All of these services can come to me in real time. You also have transactions around things like rideshare and airlines and hotels, where you're redeeming via rewards. I talked to someone at Expedia a number of years ago. It's a really interesting challenge that they have. If a purchase is made and the person gets on the plane, they are obligated to pay, right? So even if they detect the fraud afterwards, they are now in a position, it doesn't matter, the airline, their contracts obligate them to pay and to fulfill the contract for payment. And the tough challenge here is, because of the digital nature of how quickly this occurred, of how quickly the transactions can occur, the person's already on the plane, there's nothing they can do about it. The way they work that is they actually apparently will sit in an airport, book the transaction minutes or an hour before they're about to board the plane, run through security, get on the plane, and the money is lost, or the points are lost, or whatever the redemption method. Same thing with a rideshare. If I gain access to your Uber account and I get an Uber ride, you can't undo the Uber ride, right? It's just not going to happen. The last thing is digital goods purchased online, right? I buy.
I've been taking a break all day.
I'm sorry? Nope.
Wait.
Is that a question? Okay, I'll keep going. Same thing goes for the digital goods online. We talk about music, movies, content. Honestly, the most interesting story that I've heard around this, adult content. This is a really strong problem in the adult content industry, both from an account takeover perspective as well as a digital fraud perspective. Content is consumed by the threat actor, or taken by the threat actor, and no longer can be clawed back. So it's a really interesting paradigm when you start to think about the methods that this is occurring at. And what's unique here is, coming back to the point of, we've moved the control away from the presence of the instrument, and we've pinned it to the account itself. So we've essentially shifted the liability as well, right? We shifted fraudulent currency. Well, I'll caveat this. If a bank accepts fraudulent currency, the currency itself is, if the bank tanks in the currency, at that point, the merchant organization is no longer responsible for it. Same thing on the card side. If Visa says the transaction's good and they saw the card, they're no longer responsible for it. So where is the big money? The big money is in cash, credit cards, loyalty points, digital reward, online content, website access, digital wallets, right? And they all go through that common path. So why do we like this as criminals? Well, not me, I'm a good guy, but it's a high return for a minimal investment, almost no investment, depending on where they're getting their infrastructure from. So the infrastructure itself comes in from typically public cloud infrastructure, or bot networks. There are services out there that will rent you their bots on a bot per hour, count of bots per hour per utilization basis, and you pay small token Bitcoin amounts to them, and then you gain access to these large server farms that are then used to launch the attack. It monetizes incredibly easily. There is low to almost no risk of being caught in most of these attack types, unless you're having goods shipped to your own house, which probably not the sharpest criminal. And then there's limited to no law enforcement engagement at a moderate loss. So I'll give a note here to Srini's comment in the chat, which is the small transactional nature of this. And that's what I'm talking about here. When you talk about the sheer minimal nature of the transaction sizes themselves, law enforcement just isn't going to get involved. If you'd like to get engagement as a retailer from law enforcement, you're going to need to be north of $350,000 to $400,000 in attributable fraud loss. So you'll need to be able to tie that to an individual or an actor. Otherwise, they'll happily take your report and log it in a database, and it will go nowhere else. If you can build that attribution and build that case, you start to build interest from those three-letter organizations. I've seen opportunities in the past where organizations have been able to go farther on lower dollar amounts, but those involve physical losses inside of the US as well. So digital fraud that then manifests itself in an exploitation against a physical store, you can get engagements at lower amounts, but you're not going to get them at the price of a latte, the $5 cost of a Starbucks a latte, or a $25 Uber ride. You just simply, law enforcement isn't going to dig in on that problem. The other I would kind of hit on here a little bit to the comment in the chat is, it's interesting enough is that the banks have found their answer to this. They've shifted the liability to the merchant, right? So the bank is now responsible for, or the bank is no longer responsible, because the contracts say that as we take these forms of payment in the way that we're taking them, you've shifted that liability to the merchant or to the provider of the service, and that the bank is going to get reimbursed. It is going to be on the retailer or content provider to then eat and absorb that loss. So let's talk a little bit about how that loss is managed with inside organizations. Digital fraud teams. This is the most common way that it's dealt with today. The origins of these teams go back primarily to physical security organizations. So groups that were designed for what we would sometimes in the industry refer to as guns, guards, and gates, right? They're the castle walls of the physical stores. They're making sure merchandise isn't being stolen. They're making sure employees aren't stealing from the register, and they're doing investigation about fraud within inside of these stores. Because of the nature of how these teams grew up and where they grew up from, they often are not part of the cybersecurity organization. So they live inside of physical security teams or finance teams. Occasionally you'll see them in a product team. So if you have like a stored value program or a loyalty program, the fraud team will be embedded with a business organization sitting in there. They're designed kind of in a legacy construct. So they're thinking about single transaction fraud. They're thinking about these individual back and forth exchanges on a one-to-one basis. They aren't, they haven't seen in a lot of cases the capability and the way to scale horizontally by making multiple transactions at the same time. So I'll give you an example. A number of years ago, I was looking at a fraud rule set with a digital fraud team, and they had built a fraud rule that essentially said no more than 2 transactions at $50 in a day, no more than 1 transaction or no transaction greater than $100 in a day. But what they hadn't accounted for was that payment instrument could be digitally attached to multiple accounts. So they were looking at it on a singular account basis. What the threat actor had done is they had taken and created multiple accounts, and then through automation would attach the credit card to one account, hit the limit of the fraud engine, detach it, attach it to the next account, hit the limit of the fraud engine, detach it, take it to the next account. And so what the threat actor had done through lateral scaling and automation was essentially beaten what was a one-to-one transactional relationship rule set that the fraud team had created. The other part that digital fraud teams tend to work in, and this works well for buy and ship merchants where goods are going to be delivered in next day air, 2-day, 3-day air kind of scenarios, is they have these notions of manual review queues. So it's approved or it's rejected. And if I don't know it's in the middle, I'm going to put it in a review queue. And then I'm going to look at that review queue and do an analysis of it and have somebody try to drill down. That is not scalable in the modern digital marketplace. That worked well when we had catalog order forms coming in and people could spend time looking at stuff and looking at physical checks. That is not what's going to work as we scale out and we continue to grow. So let's talk a little bit about kind of our roles in this. So development teams are phenomenal. They build to requirements. They do this very well. They have also started to build, as technology stacks have scaled, they started to build highly specialized services, right? So they'll build a component of a website or a microservice that services a website. But what you'll find in like a Target, you will find that in order to create that web experience, you will have a dozen or more teams controlling individual components of the stack. And I'm not just talking about infrastructure versus code. You'll divide the code portions of the stack out, be it from the web UI experience, through the payments engine, possibly down through the cart itself. So digital checkout versus cart being two separate components run by two separate teams. And this is common in almost any large web property today. Nobody is full stack when it comes to something at the scale of a Fortune 500 or Fortune 1000 website. You have to divide those components off now. They build incredibly efficient code, right? Modern code has gone to the way of multi-threading and scaling in ways that just have not been anticipated. So when I talk about that, I talk about like elasticity of the website and how we scale things. You know, 10 years ago, when you were preparing for the holiday season, you went and built a bunch of servers and then you deployed the code on them so that you had extra capacity for the holidays. Nowadays, it's elastic, right? Nowadays, your code will auto scale based on parameters that you've allocated in your infrastructure parameters. So you might be saying things like at these transactional volumes or at this memory utilization, this CPU utilization, or at this time of day, you know, it's Cyber Monday, I want you to scale at 12 a.m. and here's what I want you to do to be ready for burst capacity. And the code is built around this. It's highly optimized for usability and uptime, and it focuses on the product team's needs. So that's a good thing. That's what it should do. It focuses heavily on what the owner for the digital property from the business perspective would say is the right thing to do. We need to sell things. We need to have a website up and running. The other part of it is it suffers from some bad security guidance. So we talked a little bit about the user early on and the fact that we've given them this tough web guidance. Well, as security product owners, in a lot of cases, we've also given similarly difficult guidance, which is making things tough. So the cyber teams. We often, so I'm on the cyber side, so I'll take a little bit of ownership here. We often have limited understanding of sales process or customer flows. It wasn't what we were built for 20 years ago. Even 5 years ago, this wasn't an expectation. So we were looking at things like remote code execution. We were looking at things about exploited vulnerabilities that were unpatched. We were looking around the IDPs and identity providers. We weren't thinking in the context of abuse of digital flows and digital properties, right? Because that's what's really happening here. It's abuse. It isn't an attack per se in the traditional sense of I'm going to defeat a security measure. We also are most commonly part of IT organizations. You'll find this in virtually all security teams. A subset of them aren't, they're broken out. But because we're embedded within IT organizations, we've tended to take an IT approach to the problem set, right? We've tended to focus in that way and think about it in that way. So let's talk a little bit about an example I'm going to walk you through here. This is a real world example. This is something that happened on a property that I was associated with at the time. I'm going to leave the names out for obvious reasons as we talk about it. But 7 years ago, this problem wasn't on anyone's radar, this notion of an automated attack at scale against a website. I was working for a company that had a very large website, you know, Fortune 500 company. The website, for no reason, sudden spike in customer activity, resource exhaustion knocks the site over. And when I say no reason, we're talking, you know, middle of February, not anywhere near the Christmas holiday window. There are no promotions going on at the time. There's nothing taking place. that should indicate, one, that consumers just suddenly decided to show up en masse, and two, that they would do so in a way that would knock over the site itself. Because what had happened here, the resource exhaustion had happened because the customers, is what it appeared, were accessing non-cached portions of the website, right? So if you've ever built large-scale websites, you typically have a CDN that sits in front of these. The content delivery network, or CDN, is responsible for delivering the bulk of the content, and then typically your back end is just going to deliver the uncached content, which is the personalized components of that. So you talk about the account components and the credit card secure components and things of that nature. You'll deliver those directly from your own content servers because they're handcrafted for each of the interactions. When we look through the site itself, and as part of the security team, security is often blamed. Please, if you're a developer in your career as you go forward, be nice to your security team, but they're often blamed as it must be security that knocked us over. That's how I was actually pulled into the problem. So we began looking at this problem with them. We looked nope, it wasn't a denial of service attack. Nope, we don't see any heavy vuln scanning across the site. No, we don't see any attempts for privilege escalations or any of the typical security threats that we would see across the site. But what we did see that was really interesting and really unique was an interesting traffic pattern. So this is a 7-day snapshot of traffic for a web platform. This is an actual web platform that is running in production. This is about a 4-year-old snapshot of that traffic. And what you'll see here was really interesting is, if I think about the context, this is 7 days. For 7 days, the volume essentially stayed continuous, barring, kind of in the middle around Wednesday, Thursday. It looks like it sloughed off a little bit, and then it spiked a little bit more as we came to the tail of the week. But website traffic flows with users because users wake up, they go to bed, they eat lunch, they have dinner, they have families, they have evenings. And so website traffic really shouldn't look like a constant. It just does, even if you're a global footprint. This particular company does have a global footprint. Your global footprint will change in size everywhere that you're at, no matter where you're at. So what should it look like? This is actually what normal traffic for a 7-day period of a typical web, consumer-facing web property looks like. You have this nice trough valley kind of pattern where you're peaking as you move through the middle of the day or the middle of the window when everybody is awake, and then people are going to go to bed and your traffic is going to slough off. You've got some night owls that are in there, but this is what the cycle of the traffic is going to look like. This is actually the slice of the traffic that was good out of what we just looked at in the analysis. So as I take you to the analysis, the yellow represents credential stuffing attack traffic. The green represents the good consumers within the site. And what you can see here is that the property itself was experiencing 70 to 80% of its traffic being a threat actor that was attempting to access customer accounts. And because this just looked like normal traffic behavior from on an individual get post kind of construct, right? We don't hold state of users over time typically in APIs or web properties. We're very transactional in how we interact with them. There wasn't anything indicating in the site flows that there was anything wrong, right? Although the web logs looked good and requests were being answered, posts were coming back, everything looked fine here. But when you actually peel away and start to do a deeper analysis, what you find is that the threat actor is actually the majority burden of the traffic here. I've seen this time and time again with company and company. I've talked to dozens of individuals in cybersecurity across the US and across the globe. This pattern, once it's identified, appears virtually in any commerce-based platform who has not directly addressed the problem. So how big is the problem? Automated attack traffic for accounts now represents the #1 attack traffic volume for websites. So this is an interesting statement to make. It is no longer denial of service attacks, right? Remember a couple of years back, we saw the Mirai botnets and things of that nature generating these massive burst flows that last for a day or two. What we're starting to see now, though, against consumer web properties is a sustained ongoing attack. Remember, we talked about that continuous revenue stream versus that one-time hit. So the attack itself has started to become very ongoing in nature and very consistent in nature. 29% of all web authentications now are automated credential stuffing, just across the board. So if you think about that number, that accounts for not just consumer retail websites, that accounts for access to tax sites, access to healthcare sites, all sorts of different web properties across the world. And each of those properties represent different values. So we talked a little early on that I was going to stay in a consumer context here, but to break that for a second when we talk about those properties, access to somebody's tax records, that represents a wealth of information associated with being able to perform identity theft, right? Any of that data that you can gain around annual income, where they work, dependents, all of those questions that you need to be able to answer in order to file for loan applications, let's say, against an individual. Healthcare records, another great example for identity theft, right? If you can access somebody's healthcare records because you've been able to gain access to their account, you now get a full and deep profile of their identity. You also know their patterns. You may know that they're not at home right now because they may be in a hospital, so identity theft is easier to take advantage of. The attack also works for more complicated attacks or complex attacks. It can be the origin of attacks that are directed not at cache anymore, but that are directed at nation state level activities. So you can see this in things like attacks against Office 365. If you know an organization is using Office 365 and you're able to attack their email and gain access to somebody's email, you're now able to impersonate them. You may be able to send communications on their behalf. You may be able to learn information. So you gain a lot here. There have been some very significant data breaches that have occurred simply through logical access of somebody's O365 or Gmail accounts done through the standard account flows, simply because they were able to credential stuff a password stolen from somewhere else and find that it was reused for a higher level privilege service. So think about, I used the same password for my airline points and I used for my work email. If someone takes that account and tries it, they just escalated into a whole new ball game from being able to access my airline points versus being able to access my work email and what's associated with that. So let's talk about defenses. Let's talk a little bit about the attack and how we deal with the attack. There's a lot of different ways that the attack itself can be thwarted. Some of them work, some of them don't work, and some of them aren't going to hold for much longer. So two-factor authentication is probably the strongest thing you can do. Give somebody a physical token, give them a YubiKey, give them a Titan key, push notifications on phone, although we can talk a little bit, that's probably not the best method going forward. There's SS7 message intercepts and things that can be done now to exploit that type of two-factor authentication. There's great implementations of horribly poorly done versions of that as well, where you give basic auth email access and then you push the notification to their inbox and it's the same credential. The things that just don't work. It can be difficult to get that type of an implementation correct. The second thing, when we switch to kind of a consumer context again, is it creates user impact. And any product group will tell you that user impact is sales. It impacts direct line of sales and therefore is less desirable, right? We want to secure the guest, but we want to do it with a method that isn't going to draw down sales. So the organization won't say, don't secure the guest. That's not the focus. They'll say, secure the guest in a way that doesn't impact their ability to transact with us. The other tough thing with two-factor auth is the first time you trust a device, you have to trust it in a basic fashion in some way initially. You have to allow the device for the first time to show up and then attach that multi-factor component to the account. You can amplify your fraud rules. You can go to that fraud team and you can say, crank up the fraud rules. What's the problem here? Well, it's cumbersome to the user because they can't see it. It's transparent to them. So if you're starting to limit transaction volumes per day to thwart your fraud losses, the user's not going to know that. They don't get a message that says, sorry, you've tried to buy too much from us for the day and therefore you've hit a fraud rule. It creates a lot of false positives. There's a lot of issues here where we can have false positives and block our best users. And that's because it treats the populations of the user community the same. right? So look at it from the construct of Starbucks for a minute. So I spent 6 years there. We knew from a guest perspective who the most consistent and frequent buyers of Starbucks coffee were. We knew that there were guests that showed up 7 days a week. We knew that there were guests that showed up once a month. If you treat the populations the same, you are now potentially taking low-risk populations who you have high level of contact with and high level of assertion of who they are, like that 7-day guest visitor, and treating them like someone you see once a month who you have less assertion of how strong their identity is to your platform. The other issue is fraud rules generally don't consider user behaviors. They don't understand things like Mike is in California today and 6 hours later he can be in Toronto. And fraud rules often are geolocation based. And so you get into constructs where you'll start to block people simply because they got on a plane and went to go see family. You just don't want scenarios like that. You have velocity rules. You can do things like limit the volume of transactions, limit the amount of products that can be bought. There's a couple issues here. They have high levels of false positives. They're easily defeated. If I want to defeat a velocity rule, I'll just spin up 10 more bots, right? If you throttle my one bot, I'll just add 9 more, right? Because from a velocity perspective now, I look like 10 different people instead of a single individual. And attackers can quickly test and tune through that. They see the velocity rules, and in 15, 20 minutes, they will test up to the limit. They'll start going, 20 transactions, nope, got a block. 19, nope, got a block. 18, oh, got through. Great, tune all the bots for 18, redeploy the code, let's go. And they'll run at that rate until you adjust again. And if you go to 17, they'll bring it down to 17. And they will continue to scale out horizontally as you continue to try to control the problem. You can restrict business flows. I can tell you this is a career limiting decision. No one's going to tell you to restrict what the company can and can't sell, but it certainly is an option. I've seen it done before. I've seen it limit careers before. You can try things like IP blocks. IP blocks are difficult to manage. They don't work. They don't work for any attack. If anybody ever tells you they're going to block an IP to fix a problem, they're wrong. They might push the attack somewhere else, but they're not going to stop it. These things just don't work. The other issue is, and I've seen this frequently in the automation world, college campuses in particular have high populations of users that are less secure in certain instances. So they maybe have unpatched laptops, they maybe have more exposure because of the frequency of locations they're visiting. And so what happens is their machines can tend to be taken over for proxy activity. Well, putting an IP block against a laptop coming from a dorm room in the University of Washington, you can suddenly block all 60,000 people at the University of Washington from accessing your website. You don't want to do that, right? You want to address the things on a more granular basis. Traditional security tools, not built for this. They're not built for site logic. They focus on virtual patching and attack vulnerabilities. And CAPTCHA, this is the one, right? This is supposed to be the silver bullet. Google's working on version 3 of reCAPTCHA. They know that their current CAPTCHA program and platform is being beat. They all are. What does CAPTCHA stand for? Most people don't know this one. Completely automated public Turing test to tell computers and humans apart. So essentially, can we devise a test that the human brain can work through more efficiently than the computer can? Well understood by users. Everyone who sees a CAPTCHA knows what they're supposed to do at this point, right? We all know how to decipher and answer the question to get through it. What's really interesting here is in 2014, Google performed a test against CAPTCHA. They took the most difficult CAPTCHAs they could find, kind of the most complicated, hard to read CAPTCHAs, and threw them at users and threw them at a trained AI computer model. Users got it right 33% of the time. The trained model got it right 99.8% of the time. So what this tells you is Moore's law is still working and the computers are still evolving, right? Computers are able to figure out these problems faster than our brains can, simply because we don't scale the way that they do. So CAPTCHA long-term, and we'll talk about this in a minute, probably isn't going to be the answer. If you actually read what Google is doing with CAPTCHA, the V3 of the reCAPTCHA, they're actually adding an anomaly detection engine behind that. We're going to talk a little bit about that here in just a minute. So, team bad guys, who are the evildoers of the world? Generally, from a retail perspective, it's organized crime, right? If it's somebody from a nation state going after O365, that certainly is a different game. Financial institutions, primarily organized crime, some nation state activity here. But generally, as a rule of thumb, account takeover is either focused at that nation state, high level penetration into an organization, or severely or significantly advanced threat actors. So think of your Fin7s of the world coming after large retail corporations in order to take high volumes of credit cards and things of that nature. Bulk of the volume of this traffic you're looking at is organized crime or small organized criminal groups that are looking for stable cash flow. They just want to make money like the rest of us. They can operate these attacks from anywhere. They don't have to be within inside of our borders. Interestingly enough, I've seen people look to do things like block ASNs. I'm going to block the ASNs of China because China shouldn't come to our website. What's really interesting about that is the origins of the attacks. You usually don't use infrastructure out of country. They'll typically use infrastructure domestically here because they'll use public cloud infrastructure like Amazon or Google, or they'll use proxy infrastructure that they're able to obtain on Comcast's network through user penetrations, things of that nature. The stolen goods get monetized online very easily. They do interesting things like they'll take the compromised accounts and actually have the merchandise just shipped from that account directly to individuals that have bought it online. I've actually seen instances where they'll advertise the merchandise for sale that they haven't acquired yet, and then when the good person buys it from them on a Craigslist or an eBay or wherever, they'll then immediately go to an account that they've taken over and they'll ship that merchandise from that taken over account directly to the good individual, basically absolving themselves of needing to touch that merchandise. And hey, the plus side of being a bad guy is you generally get to work your own schedule. It's not a 9-to-5 job. So let's look at some of the tools. What are some of these kind of interesting tools that they're using to exploit and launch these attacks? We talked about CAPTCHA. The answer to CAPTCHA is death by CAPTCHA. It is a SaaS service that will answer CAPTCHAs for the bad guys. It comes in 2 flavors. You can do you can use the AI-based engine to answer the CAPTCHA for you, or in the instance of CAPTCHA that the AI-based engine is not doing a successful job at, they actually have manual teams that will answer the CAPTCHAs. And these are teams that are based in offshore countries. So you can think of places in Asia where manpower is cheap, and they will have people that will literally sit there and answer the CAPTCHA requests that are proxy to the platform for the users. $1.39 is their starting price for 1,000 CAPTCHAs. They advertise it on their website. And this problem has been solved, right? So if automation can't deal with it, they'll do it for you by hand. But this is a tool and this is a website that any of you can go to today. I wouldn't recommend you start cracking people's CAPTCHA. There are some legalities associated with that, but it is out there, and this is one of the vectors that is used to defeat things like CAPTCHA. But what I really want to talk about is the automation itself. So the automation of the attack, there are a lot of different ways that we can automate and attack websites. We can write our own custom code. You can write, Python scripts. You can do lots of different things here. Or you can download the most commonly sold and used tool on the internet, Sentry MBA. This is a publicly available tool that is designed to perform automated attacks against retailers' websites. You'll need a few things to leverage the tool. There are YouTube videos online that will actually explain to users how to use the tool. You download the tool, you bring a list of proxies, so you go rent some proxies from somewhere online. You get a site configuration. These are a little tougher to get depending on the complexity of defense measures at the site. So a proxy configuration for an out-of-the-way retailer, small private business retailer is probably going to be a little bit cheaper because they don't have defense mechanisms versus a large financial institution or a large retailer like a Target or one of those, a Nike, something like that. But you get your configuration, you get your list of proxies, you set your parameters. What's really interesting about Sentry MBA is it has the ability to do some complex things on its own. It can actually solve CAPTCHA on its own. It's got a CAPTCHA engine in it. It can also link out. So you could link out to death by CAPTCHA if its engine's not able to perform and able to answer those CAPTCHAs as it's performing the activity. It can do interesting things like user agent string rotation, We're going to talk about that here in a second and why that's important. But essentially what it boils down to is users and user populations move in known patterns. This is how marketing works. This is how Google is able to kind of figure out, how well a marketing promotion or offer is doing, because we see patterns of behaviors in users. And what I mean by that is we'll see roughly the same percentage of iPhone users, roughly the same percentage of Android phone users, and in the same percentages of OSs on a day-by-day basis. So Catalina is the most current Mac OS, and you probably, your site might see 40% Macs. Of the 40%, 78% are running Catalina, 10% are running an earlier version, and 5% are running the latest release, which is Big Sur. And you see those population metrics, and they hold stable. Those user agent strings associated with those metrics of population, Century MBA is able to impersonate those, and it's able to try to replicate population variances. And things like this become critical because when you automate an attack against a website, you need to look like the general population. You need to look like that distributed, you want to hide, right? You want to basically look like everybody else. You don't want to stick your head out and say, here I am, I'm the bad guy. So let's talk about those patterns and the behaviors and what that means like. So we've got to move beyond when we start to deal with these attacks, and this is why it becomes big from a developer perspective. We have to move beyond the traditional security's handled by fraud, security's handled by the security team. I don't have a conversation at the table. I just build a website and they put up appliances around this thing or a service next to it as a sidecar and they protect me. That doesn't work anymore. These tools like Century MBA and Death by CAPTCHA, as they come forward, they're starting to attack in such a way that it isn't scalable from a security perspective to intervene or a fraud perspective to intervene without starting to create impact to users. What we have to do is we have to start looking at this in a machine-driven method. So we have to start looking at anomaly detection and pattern deviation, and we have to start looking at it with some user context associated with it. Historically, we haven't done that in websites, and the tough challenge here is the platforms that are capable of doing it are the serving platforms themselves. The tools that sit on either side aren't able to bring as much intelligence to bear without having to jump through incredibly complex hoops, or may not even be possible to jump through those hoops and open those doors. So when we talk about it, what do we want to look at? Well, we know that users interact with the site in a consistent pattern in a consistent way. This is how marketing works, right? Back to that, this is how Google knows a promotion works and how your sales teams will sell things. We know that the user starts at a specific point in the site. We know that their behavior may be to click on a contextual menu for products or go to a search bar. We know that when a page renders, they'll dwell on the page for a certain amount of time on average. And there are standard deviations inside the user population that hold constant associated with those activities. Return users are even better. If I'm a frequent shopper of Target.com, I will have a pretty consistent pattern of how I do it. I know I want to go to grocery. I know I want to set up my order so that I can pick it up curbside. And I have a pretty consistent pattern of how I'll flow through the site. I don't show up, not navigate the UI, put a TV in my cart and immediately check out, right? That's not a pattern for me. That's not a pattern for a standard user. We have to start looking at those deviations and start to understand how we identify users as human or automated at a different level, because we can't do it from the front door where there is no state. Users also generally present common traits across the population. So we talked about the user agent strings. They also operate in ways that are geographically linked as well, right? So East Coast wakes up before West Coast does. IP addresses in those range should come online earlier. User behavior should mimic the activities of a waking population. People generally don't wake up at 5 a.m. and buy 50 gift cards and ship them to different locations, right? We know what users' activity should look like. We might see more of that as it comes to the holidays, but we're not going to see it at 5 or 4 in the morning, right? So we have to start looking at the data analytics of the problem to be able to identify these activities in a different way. It can't just be the authentication mechanism anymore. We also need to look at the various tools that are built with inside of the stack. So we have things like API gateways, typically in most modern web stacks or API stacks. we need to be able to look at those API gateways as places where we can peel away these patterns of traffic and patterns of behavior. We also need to look at things where we start to issue key pairs on a session-based context basis. So this could be a cookie in the notion of a website, or it could be session keys that are issued with inside of an API and a heavy mobile app, a fully functioned mobile app that you have. But we have to figure out ways to push deeper down this equation and farther down, because we won't be able to control whether or not a simple authentication is the answer. And the last thing I would say is forcing the bad guy to look like the good guys, horrible idea. We want them to stand out. We don't want to consistently smack them at the same point in time. We want to allow some of the signal that surfaces to exist in our platforms, and we want to find new and unique ways to manage it. So if we recognize we received a credential stuffer from a bad actor, the notion of a honeypot applies just as equally to a web property as it does to a VM sitting exposed in a DMZ on the internet. We want to give the threat actor a little bit of time to play and to poke in a safe and contained way, so that we can learn more about the objectives of where they're going, which gives us more levers to pull and how we stop them. So some of the key things that we've got to move forward as you start to move through your careers and you start to take things back and look at the way that you're going to either join the workforce or go back to the workforce and apply these kind of concepts and principles. Security teams, first and foremost, we have to look beyond traditional security. We are no longer just making sure patches are there, passwords are strong, mail is filtered effectively. By the way, the 4 best things that any security team can do, and do them well for your organization: filter your email, control your identity access points that are externally exposed, keep your antivirus installed, and patch. Make sure you're patching stuff. If you do those 4 things really well, you're going to be ahead of most of the pack. Fraud teams need to dig deeper into the understanding of cyber attacks. And the other pivot you're seeing here is fraud teams are now being incorporated into cybersecurity operations centers, fusion centers. You're also starting to see cyber teams being moved into the IT organization. This is a good thing. It's helping them become more modern. Development teams need to engage the security and fraud organizations early on. You need to take the requirements that you're receiving from the business, and you need to then go to the fraud and the security teams, and you need to talk to them about abusability. So if you're going to build something and you're going to stick it on the internet, you need to realize that abuse is going to happen to this thing now. And how do you help prevent that? How do you write that natively into the code? It is a lot easier to put something in pre-deployment than it is to, under duress, try to modify a site property in real time. The last kind of parting words I'll leave. If you've automated a test of your site or your platform, someone else is going to do the same thing. If you stick it on the internet, it's fair game. Within days or hours, someone will do the same thing. Automation is cheap and almost free. They're going to consistently do this. Secure applications are vulnerable to attack, as we've talked about today. So we've talked about abusability versus attacking security. Those are 2 different things, the abuse of the cyber platform. If the site itself, let me phrase this slightly differently. Sticking a secure application on the web, out on the web, and saying, I've hardened this, I've built the requirements. You're not doing the business a service if the customers are still being negatively impacted. The customers won't return if the fraud is occurring. If the cyber attack and account takeover is occurring, or the other attacks are occurring, the customers will eventually leave, and you'll see this time and time again. The last thing I would say is just kind of to refresh the point. Cyber attacks that are about abusability do not leverage UIs. They leverage the underlying APIs, which means they don't follow the flows of the site. A good example I've seen of this is a large retailer who built a multi-factor authentication step up into a mobile application as an asynchronous call to the transaction itself. So you would actually, the user would be working through the purchase flow. You would do a step-up auth call on the side, but it was not synchronously linked to the purchase flow itself. So if you didn't use the mobile app and you didn't make the security call, the transaction would still process. So you have to think about the construct of how the automation and net abusability works. Things have to be linked together as if the UI or the customer flow doesn't exist. So with that, I have spoken a lot. I will open it up and say, what kind of questions?
This was actually from earlier, but would you recommend LastPass with auto-generating passwords for every user?
Recommend something. I LastPass is fine. I use an application called Codebook. I like it because it's not cloud-based in the way that it syncs, but you know, some type of password manager.
Mm-hmm. I just get yelled at by my wife because she never knows what like the Netflix password is.
Fair. That's totally fair.
Here's one. I hear a lot about how quantum computing will impact the security field. I'd love to hear that from you.
It's an interesting thing when we look at problems like this. I think quantum computing's direct effect is going to be initially against things like encryption, right? Because you're able to perform the calculations to crack and create the collisions much faster. Yeah. I don't know that you're going to see it necessarily applicable here because there will be limitations of bandwidth and other things that throttle the ability to do this type of activity against a site.
Yeah, because you can only attack as much as you can throw at a website, and that's a bottleneck.
Yep. Yep, you're just limited by the front door. But when you start talking about encryption, I think quantum computing is a challenge, a very large challenge for that. Other questions? Awesome.
I have one. It's John. So you talked about a lot of these attacks being using stolen credentials. I'm just wondering if there's a sense of is it more stolen credentials or is it just password guessing, or are they like, you know, how does that break out in percentages, or are they somehow breaking into traffic and then somehow stealing the user credentials at runtime?
There are two types of actors that are out there that are launching these attacks. So there's the stolen or spilled credential actor, and then there's the sophisticated actor that performed the data breach. And so what you'll tend to see, well, and there's a third category. I'll talk about that in a second. So let's talk first about the most skilled adversary. These are people that have breached another corporation, have dumped a username and password list, and then are now taking that list out to sites. They will shop that list by themselves for their own personal gain. And then at the end, they will spill that out onto the internet to, you know, for bona fides to get their cred up, their street cred up with the rest of the threat actors to go, here's a list, and essentially throw the slim pickings down to the, you know, the kid in mom's basement that's going to use less sophisticated, less structured attack methods to come after your site, right? So those are category 1 and category 2 threat actors. You've got the person that got the list first that then shops it on their own, and then they throw it down to the kind of the masses to then try to play with. You also see some activity around top 10 passwords. And I've seen this before where they'll take and they'll look at the site lockout parameters of a site. And if, a good example of this is sites that use email address as the username. If you know somebody's email address and you know the top 10 common passwords, you can throw the email address of the password, and if the lockout is 6 attempts, try it 5 times, and then come back in a month and continue to try 5 times, right? So try the first 5 common passwords, come back in a month and try the next 5 passwords. And essentially what you're trying to do is to create enough time between the first 5 attempts before account lockout and the second 5 attempts with the 10 most common passwords to basically have the counter reset so that you don't collide with the account lock itself, because the last thing you want to do is lock 100,000 accounts somewhere and throw up the flag that you're attacking the site.
I had a question. So what's a good source to find out about the latest data breaches so that we can, keep our passwords up to date and change them as soon as possible?
Have I Been Pwned is a great website. You should register and you should monitor your credential there. Generally does a pretty good job of all of the spilled credentials that are available on the internet. I register, I've got a personal domain that I've also got registered there, so I can see if any of the domain accounts that I have associated with it are spilled as well. Target can do the same thing. I would certainly start there. That's probably the best way. What I would say is by the time credentials have hit a place like that, they've probably already been shopped for account takeover activity by the sophisticated actor that stole the information.
Cool. I also noticed Google Chrome actually added this new feature where it shows like some of the breached passwords as well. So that's why I brought it up.
Yep. Yeah, it's an interesting feature actually. So NIST changed their guidance. There's been this big debate in the industry for about 3-4 years now of should we hold on to these stolen password lists or should we check them against our database, right? Should we preemptively check? And what does that mean in the context of holding stolen property, right? Because the credential was stolen property when it was removed. Should you maintain a database of that stolen property so that you can make sure that users don't use those credentials on your site? Google and some other organizations have started to work through hashing algorithms where they can then do database checks of your hashed password against a non-reversible version of the password that they're keeping as well to then see if it's been reused somewhere. So yeah, you're definitely starting to see that. I think NIST changed the guidance and started encouraging that about 2 years ago.
Hi, I'm curious about the challenge of finding illegitimate activity that was made through legitimate means, like for instance, like a scam or something like that.
Are you talking on a technical level, how we would go looking for that? Yep. So there's a couple things that it would do. We obviously would be looking for broader bases of transactions versus singular transactions. So there are some simplistic parameters that you can start to look for early on. Century MBA, shockingly enough, by default uses 4 common user agent strings. And a lot of the kids that are playing in mom's basement don't know that they need to change those. So they're going to stick out like a sore thumb if they attempt to use Century MBA without using a user agent string list in some type of a pattern. So you can look for basic parameters like that. Unsophisticated actors are also going to use common IPs. They're going to come from locations that are going to make them stand out. If you wanted to do wide swath looks for more sophisticated threat actors to maybe find botnets, you would look at your site in ways you could still use IPs, but you need to be able to correlate data on a much larger scale and time frame. So you generally know that household like a Comcast ASN based or Xfinity based ASN, you should only see that IP at your site, 1 or 2 visits per day. You shouldn't see it 50 times over a 10-hour window, right? So that could give you indications that if you see hundreds or thousands of Comcast addresses coming in 50 or 100 or 200 times within a given window, that you've got a threat actor that's using a botnet based on home-based devices that they've compromised that are coming at you. And that's a great way to kind of look for some of those problems because Xfinity and Comcast stick out pretty good. You kind of know that home-based users generally, gaming sites aside and potentially adult content sites aside, but if you're operating in a retail space, your good customers aren't showing up to target.com 50 times a day over the course of a 12-hour or 10-hour window to log in. You just know that's not true. Any other parting questions before we come up on time here? All right, I appreciate the opportunity to speak to everybody today. I didn't bring my LinkedIn and other details in my slide deck, but I am certainly available on LinkedIn and you can reach out to me there as the best way if you have follow-ups or want to learn more.
All right. Thank you, Mike. And thank you everybody for joining us. This is, like I said, the last one in this industrial seminar series for the year. We'll see those of you who are not students, hopefully next fall. And everybody else, good luck with the end of the semester, and we'll see you all in the spring.
See ya. Thank you.